Okay, I want you to picture something for a second. Imagine a vast, glowing cosmic ocean stretching endlessly in literally every direction. A space so perfectly smooth, so uniform, that there are absolutely no stars, no galaxies, and definitely no life. This is the universe in its absolute infancy. But obviously, look around us today, right? We live in a cosmos that is just packed with structure, complexity, and undeniable beauty. So, how on earth did we get from that smooth primordial soup to the majestic cosmic web we see tonight? Well, welcome to today's Explainer, where we're going to embark on an awe-inspiring cosmic zoom to trace what is arguably the greatest origin story ever told.
Now, you might be wondering, and honestly, it's the ultimate question of cosmology. If the standard model says the early universe was almost perfectly uniform, where did all the stuff come from? Because here's the thing, that standard model is definitely missing a critical puzzle piece. If the universe was 100% completely smooth and homogeneous, there'd be no gravity pulling matter together into clumps, which means no stars to forge carbon, no planets to host oceans, and absolutely no observers around to even ask these questions.
So what's the missing piece? It all boils down to this profound realization from our source material. Inflation transforms microscopic quantum fluctuations into macroscopic seeds for cosmological structure formation. That one single sentence is basically the entire narrative arc of our explainer today. We're going to dive into exactly how the absolute smallest things in nature literally created the largest structures in the entire cosmos. It's a wild ride.
All right, let's get into it. Chapter 1, The Smooth Cosmic Ocean. If we travel all the way back to the very beginning, general relativity models the universe on incredibly large scales as this homogeneous, isotropic, perfect fluid. Physicists call it an FLW universe. But if that macro assumption was the whole picture, well, we simply wouldn't exist. The microreality dictates that tiny, microscopic imperfections absolutely had to exist. So we really need to view that smooth FLW baseline as just a blank canvas, a canvas upon which tiny, crucial perturbations are added. Which brings us right to Chapter 2, Tiny Quantum Fluctuations. Let's zoom way, way down to the subatomic scale. Spacetime here isn't just empty nothingness, it is literally bubbling with quantum mechanics. If we look at the inflaton field, we see what are called zero-point fluctuations. They're these tiny, totally erratic ripples on the potential curve of a scalar field. And these minute variations in energy density, which are happening at scales so unbelievably small we can barely wrap our heads around them, are the rawest, earliest seeds of absolutely everything you see in the night sky. Moving right along, Chapter 3, Inflation and Horizon Exit. So how do a bunch of subatomic quantum ripples eventually become the blueprints for entire galaxies? Well, they need an explosive trigger. Just a tiny fraction of a second after the Big Bang, the universe underwent this violently rapid period of exponential expansion. We call it inflation. Now, our little quantum ripple starts out super small, or subhorizon, but inflation expands space-time faster than the speed of light itself. It stretches this tiny subatomic ripple to an absolutely massive cosmic scale. It gets stretched so big that it's larger than the observable horizon. And once it undergoes this horizon exit, causal physics can't act on it anymore. It just completely freezes in place, locked in as a permanent macroscopic seed. Now for a bit of the math side. Chapter 4, Resolving the Gauge Problem. You see, mathematically tracking these frozen ripples through time, it presents a massive theoretical challenge for physicists, known as the gauge problem. When they try to calculate how these perturbations evolve using general relativity, it's honestly like trying to look at the universe through a really distorted, wavy lens. Just shifting your coordinate grid can accidentally create fictitious density perturbations that aren't actually there at all. It's a total mathematical illusion. To fix this, physicist James Bardeen introduced something called gauge-invariant variables. Think of them as a pair of corrective glasses that let us strip away all those coordinate illusions so we can finally measure the true physical clumps of matter. Fast-forwarding a bit, Chapter 5, The Cosmic Microwave Background. Okay, so inflation has ended, the universe is cooling down, and those frozen ripples we talked about earlier finally re-enter the cosmic horizon. The result of this is the Cosmic Microwave Background, or CMB. It's basically a thermal baby picture of the universe, taken when it was just 380,000 years old. Those colorful temperature variations you see, they map directly back to that primordial density field. As the ripples re-entered the horizon, gravity started pulling matter into the dense, clumpy regions, while radiation pressure pushed right back out. This tug-of-war created massive acoustic oscillations, literally giant sound waves ringing through the cosmic plasma. And the crazy thing is, those sound waves left a signature that we can measure today. When you look at the acoustic peaks in the CMB power spectrum, it's just breathtaking. Why? Because those peaks prove that inflation coordinated the phases of all these primordial ripples. When they froze out during inflation, they essentially synchronized. So upon re-entering the horizon, they started oscillating together like a perfectly coherent cosmic symphony. The exact heights and spacings of those peaks actually give us the precise recipe of everything contained in our universe.
Which sets the stage for our final act. Chapter 6, Birth of the Cosmic Web.
How exactly do ancient thermal spots gravitationally collapse into the vast modern structures we know today? To understand this cosmic architecture, physicists use something called scalar vector tensor decomposition. It's a clean way of breaking down complex metric perturbations into a simple rule of three. First, you have scalar perturbations. These are the density clumps that act as the actual gravitational seeds for galaxies. Second, vector perturbations, which are just rotational flows that quickly decay away and disappear. And finally, tensor perturbations, which are literal gravitational waves stretching and squeezing the very fabric of space-time itself.
Now, because the light from the CMB is polarized, these perturbations leave distinct visual signatures we can hunt for. Scalar perturbations, the ones building the galaxies, only create these pinwheel-like patterns called E-modes. But tensor perturbations, those primordial gravitational waves, they create both E-modes and these swirly, distinctive B-mode patterns. And let me tell you, detecting these specific B-mode signatures is basically the holy grail of modern cosmology right now. It is the ultimate smoking gun that would unequivocally 100% prove the theory of inflation. Over billions of years, driven by what we call Einstein-Boltzmann evolution, the math literally translates into reality. The dense spots from our ancient CMB map start to gravitationally collapse. Dark matter halos form first, creating this incredibly massive invisible scaffold. And then ordinary baryonic matter, the gas and dust, falls straight into those deep gravitational wells, lighting up as the very first stars and galaxies. This cascading process forms the incredibly stunning large-scale structure known as the cosmic web. When we put the whole journey side by side, it's just amazing. On one side, we have the ancient thermal map of the early universe. On the other, the gleaming, complex galaxies of the Hubble Deep Field. That ancient modeled map is literally the direct architectural blueprint for the incredibly beautiful and complex universe we inhabit today.
Which lays us to this final, wildly provocative thought. If every single galaxy, every star, and every planet was seeded by a tiny, erratic subatomic fluctuation in the very first fraction of a second of time, are we simply the macroscopic echoes of microscopic quantum noise? It really shows that the physics of the incredibly small is intimately, undeniably bound to the physics of the unfathomably large. In a very real way, we are the universe structured by quantum mechanics looking back at itself. Thank you so much for joining me on this explainer. Until next time, keep looking up and keep wondering.